Welcome to Chapter 14. We're going to be doing what I call double integrals, but sometimes textbooks will call them iterated integrals. And so that's where you'll have multiple integrals to the same function, but you're changing with which variable you're going to take the integral with respect to. So let's look at this first integral. I've got the integral from 1 to 2y of 2xy dx. This part right here tells me that x is my variable, which means all the y's are treated as a fixed constant. So if I were to take the integral here, I could take 2 and y out, and then I've just got the integral from 1 to 2y, remember y is a constant, of x dx. Well, the integral of x is x squared over 2, and then times 2y here. So the 2's cancel, and I'm left with yx squared from 1 to 2y. And now I can plug in my limits here. I've got y times 2y squared minus y times 1 squared. So I end up with 4y to the third minus y. And that's my integral. If I look at the second example, now I'm evaluating it with respect to y. So x is my constant. So I'm going to take out the 2x, and I'll have 1 to 2x of y dy. The integral of y is y squared over 2 times your 2x, so the 2's cancel. So now I have xy squared from 1 to 2x, and I can plug in my limits now. X times 2x squared minus x times 1 squared is going to be 4x to the third minus x. So let's look at a couple more examples. On this page, you've got the integral with respect to y right here. So that means every time you see an x, that's going to be a constant. So let's take the integral here. The first section here, 2x squared y to the negative 2. Remember, 2x squared is a constant. Add 1 to the exponent and divide by your new exponent. And the second one becomes 2y squared over 2. I'm going to simplify that just a little bit. Negative 2x squared y to the negative 1 plus y squared. And I'm going to evaluate that integral from 1 to x. So now I'm going to plug in x for all the y's. So I've got negative 2x squared x to the negative 1 plus x squared minus negative 2x squared times 1 to the negative 1 plus 1 squared. And I can just simplify my algebra now. I have negative 2x plus x squared plus 2x squared minus 1, and I can combine like terms here, 3x squared minus 2x minus 1. That's your final answer. Let's take a look at another one. Now we're going to have what are called iterated integrals, where you've got two different integrals together, and you're going to be taking one integral with respect to x and one with respect to y. The key here is to work from the inside out. So right now I've got the dy first, so I'm going to do the y integral first, and then I'm going to take that answer and take the integral of that with respect to x. So now let's work from on the inside part first. I'm going to ignore the outside part for right now. I'm just going to do this integral from 1 to x of 2x squared y to the negative 2 plus 2y, which we just took this integral here. So I'm going to do it kind of quickly. we've got 2x squared y to the negative 1 over negative 1 plus 2y squared over 2, which simplifies to negative 2x squared y to the negative 1 plus y squared. Again, I'm just going through this quickly because we just did this example from 1 to x. And that when we do our math, we end up with 3x squared minus 2x minus 1 when you do that integral. So now I'm going to take that answer and do the outside integral. The outside integral was the integral from 1 to 2 with respect to x. And when you do double integrals, there's a lot of really neat applications of this. And so the purpose of doing multiple integrals is to eventually get rid of the variable. So you'll use this when finding area or volume, where you're going to have a number as your final answer. So when you just do one integral of multiple variables, you kind of have an unfinished product there. And so you keep taking integrals with respect to different variables until you're left with just a constant. So now what's going to happen in this one is we're going to get rid of all the x's. So let's take this integral here. This becomes 3x cubed over 3 minus 2x squared over 2 minus 1x from 1 to 2. So let's simplify that just a little bit before we take our integral. X cubed minus x squared minus x from 1 to 2. So this becomes 2 to the third minus 2 squared minus 2 minus 1 to the third minus 1 squared minus 1. So 8 minus 4 is 4, 4 minus 2 is 2. And 1 minus 1 is 0, minus 1 is negative 1. So minus a negative 1 is plus 1. So it equals 3. And that is how you do an iterated integral. We're going to discuss some rules and best practices on the next slide. The best advice I can give to you when doing integrals is to draw a picture. So if a lot of times it's not going to give you the integral to start with, it's going to ask you to find the area bounded by a set of parameters. And so, for example, it might just give you this one: find the area of the region bound by the function y equals x goes from 1 to 2, and y goes from 1 to 2. And so you would draw all three of those boundaries, and you can see that the region that's enclosed by all three of those parameters is the yellow part right there. And so when you're setting up integrals, it doesn't matter which one you draw first. You can do the x integral first or the y integral first. That part doesn't matter as much as long as you're keeping the parameters in the correct order. So let's do it with respect to y first. Okay, so we're going to take the integral with respect to y. So that means that I've got, I'm going to be going vertically right here. So you could think about drawing a rectangle. Think of the Riemann sum. So that's a vertical integral, so we'll be integrating with respect to y. So my inside integral is going to be the y integral, since I'm doing this with respect to y first, and I did a vertical rectangle, think Riemann sum. So my inside integral is going to be dy, and my outside integral is going to be dx. So we're just taking the area of a flat surface, so there's not going to be anything here yet. So think of that as just a constant. So my boundaries for y, I go from 1, I start at 1, and I go up to my function. So I'm going from 1 up to x. Think like y equals x, the function y equals x. And then my outside function, the x part, the boundaries are from 1 to 2. So that's how I set up my integral with respect to y. So with respect to x, then, you've got my inside integral is going to be dx, and my boundaries now are going to make a horizontal line. So here's my rectangle that I'm thinking of. And so I go from my function to 2. But now this is with respect to x, so I've got to solve my function for x equals. So this would be y. Think x equals y. And then my outside function is dy, and my y is bounded from 1 to 2. And so if you take the integral of this, you would get the area of that yellow region. And we're going to do some examples of actually calculating the area in just a second. So let's take a look at the next example. We've got two different regions drawn here. One of them is going to be easier to solve using a vertical integral, and one is going to be easier to draw with a horizontal integral. So if I'm looking at this first one, I have to go from function to function, so my Riemann rectangle is going to be like this. So this is a vertical type area, so that means my inside integral is going to be y. So my inside integral is going to be y, and my outside integral is going to be x. And so my y integral goes from the first function to the second function. So it goes to g1 to g2, like that. And then my second boundary with respect to x goes from a to b. So this is just practicing setting up, practice setting up your integrals. Let's take a look at the second one. This is going to be a horizontal rectangle here, so I can draw my rectangle going this way, my Riemann sums. So I'm going to do this inside integral with respect to x, and it goes from h1 to h2, and my y boundary is from c to d. And so that's how you would set up the area equation or the area integral for a horizontal integral. So now we're going to actually start doing some integrals here. So find the area of the rectangle using iterated integrals. So we know that this is b minus a, that's the width of the rectangle, and the length of the integral is d minus c. But we're going to do this the long and complicated way. Instead of just multiplying length times width, we're actually going to do an integral. We're going to set up an integral. So it doesn't matter which one you do. So I'm going to do it with respect to y first. So my rectangle is going to be a vertical rectangle here. So I'm going to take the integral with respect to y first, and y goes from c to d, and x goes from a to b. And so now I'm going to do the inside integral first, right here. So the integral of that is going to be y from c to d. So that becomes d minus c. And then I'm going to take the integral of a to b dx. So d minus c, that's all still a constant. So the integral of that is d minus c x from a to b. And so if I plug in my limits here, I've got d minus c times b minus d minus c times a. And to make that just a little easier, I can rewrite this as d minus c times b minus a. And so we know with geometry that that really is the area of that rectangle. But now we've taken the integral and proven it. All right, let's look at this other one where they didn't draw the picture for you first, but like I said, you always want to draw a picture because you can see the boundaries better. So we're going to find the area of the region bounded by y equals sine x and y equals cosine x. So first we need to draw a picture. So I'm going to try to draw this as neatly as possible. I'll draw sine x in red. So sine is like this. And I can put my boundaries. This is pi over 2, pi, 3 pi over 2, 2 pi, obviously 0. And I'm going to graph my cosine function in green. So this is 1 and -1 down here. So I'm going to have this. Let me draw that better. Alright, so there's our cosine function. And so now you can see where the bounded region is in the middle there. This is the bounded region they're talking about. So we want to find the area of that region. And so I'm going to figure out the intersection points here. This intersection point is at pi over 4, and this intersection point is at 5 pi over 4. And so let's write our boundaries as a inequality for x and inequality for y. So my x boundary is from 5 pi over 4 down to pi over 4. That's what x is bounded by. And y is bounded by the function, the bottom boundary is cosine x and the top boundary is sine x. So just looking at it, since y has sine and cosine x involved, I'm going to do a vertical rectangle because my inside integral has to always have the variables. And so I'm going to have dy go first. So my integral of dy, and then I'm going to have my dx integral. So my y boundary is from cosine x to sine x. And my x boundary is from pi over 4 to 5 pi over 4. And now we can evaluate this integral. So if I do the inside part first, I'm going to have the integral of a constant is y from cosine x to sine x. So that equals sine x minus cosine x. And now I'm going to take the integral of that with respect to x. So now I have the integral of sine x minus cosine x dx from pi over 4 to 5 pi over 4. The integral of sine is negative cosine, and the integral of cosine is sine from pi over 4 to 5 pi over 4. And so now we can evaluate it. I've got negative cosine 5 pi over 4 minus sine of 5 pi over 4 minus negative cosine pi over 4 minus sine of pi over 4. Negative cosine of 5 pi over 4 is negative of negative root 2 over 2, so that's root 2 over 2, minus sine of 5 pi over 4 is root 2 over 2, so that becomes plus root 2 over 2. Negative cosine of pi over 4 is negative root 2 over 2, and then minus root 2 over 2. And so now I've got 2 root 2 over 2 minus negative 2 root 2 over 2. The 2's cancel. So now I have root 2 plus root 2, which is 2 root 2. So from start to finish, I drew my picture, I set up the boundaries right here. I wrote an integral to find the area. Remember, the integral to find the area, there's no function in this little space right here. With the correct boundaries, I took the integral and I have my answer. This one's a little more complicated, and you'll see what I'm talking about once we draw the picture. So it says the area of the region bounded by the parabola y equals 4x minus x squared above the x-axis and above the line negative 3x plus 6. So we're going to sketch a graph of this region. And so this parabola has a y-intercept of 0 and a maximum height of 4. You can always check what this graph looks like in a calculator if you don't feel like doing it by hand. Just know that you might not always get to have a calculator. So 1, 2, 3, 4, and it has another 0 at 4. So I'm going to try to draw this well. It has a maximum here. There's our parabola from 0 to 4. And the line has a y-intercept of 6 and a slope of 3. Just pretend like that goes there. That intersection is 1, 3, by the way. So we're trying to find this shaded region right here. And you'll notice that there's no clear boundary. You can't do just one integral because there's two different functions that have this boundary. So here's your y equals negative 3x plus 6, and this is y equals 4x minus x squared. So what you have to do is split it into two different regions right here. So we've got region 1 and region 2 right there. So you have to have two separate integrals because you need to be able to have a constant interval. You can't just say from 0 up to the parabola because then that includes this. So you don't want to do that type of integral. So for region 1, my integral, I'm going to do a vertical integral here. So the bottom of my y is the line negative 3x plus 6, and the top is 4x minus x squared. And then I'm going to do dx, and the bottom is 2, or sorry, the bottom is 1 and the top is 2. So I'm going from 1 to 2 for x, and I'm going from my line to my parabola for y. Region 2, I'm also going to do a vertical integral here. Region 2 for dy goes from 0 up to my parabola, and from 2 to 4 for my x. And so you're going to evaluate these two integrals separately and then add them. So let's evaluate these integrals. For region 1, I've got from 1 to 2 and from negative 3x plus 6 to 4x minus x squared dy dx. So the inside integral becomes y from negative 3x plus 6 to 4x minus x squared, which gives me 4x minus x squared minus negative 3x plus 6. I'm going to simplify this. I've got negative x squared, and then 4x plus 3x is 7x and minus 6. That's the inside integral. So now I can take the integral with respect to x. So from 1 to 2 of negative x squared plus 7x minus 6 dx. So this becomes negative x cubed over 3 plus 7x squared over 2 minus 6x from 1 to 2. So now I've got negative 2 cubed over 3 plus 7 times 2 squared over 2 minus 6 times 2 minus negative 1 cubed over 3 plus 7 times 1 squared over 2 minus 6 times 1. And when we simplify that, we get negative 8 over 3 plus 28 over 2 minus 12 minus negative 1/3 plus 7 over 2 minus 6. And all of that is going to be 13 over 6. So that's the area of region 1. So now we've got to go back and find the area of region 2. So region 2 had the integral from 2 to 4 and 0 to 4x minus x squared of dy dx. So the inside integral is going to be y from 0 to 4x minus x squared, which is 4x minus x squared minus 0. And then I'm going to take the integral of that from 2 to 4 with respect to x. So now that becomes 4x squared over 2 minus x to the 3rd over 3. I'm going to simplify that a little bit. 2x squared minus x cubed over 3 from 2 to 4. So I've got 2 times 4 squared minus 4 to the 3rd over 3 minus 2 times 2 squared minus 2 to the 3rd over 3. We can do some mental math here. So 16 times 2 is 32 minus 64 over 3 minus 8 minus 8/3. And when we type all that into a calculator to save time, you get 16 over 3. So that's R2. And so if you add region 1 plus region 2, you get R1 plus R2 is 13 over 6 plus 16 over 3, which ends up being 15 over 2, or 7.5. So that's the area of the bounded region and your final answer. So I'll zoom out just so you can see everything from start to finish. We had to separate it into 2 regions because of the way the boundaries worked. I needed to have the same bottom region all the way across. And so I couldn't use the bottom region of 0 and the bottom region of the line. So I had to separate it into 2 separate regions. I set up an integral for both of those regions. I took the integral of each and then added the 2 regions together, and that gave me the total area of the region. On this page, I've got 3 practice problems that I want you to try, and I'm going to post the answers to this so that you can see how you did. And you're also going to have some book problems to work on. On Friday, we will continue working on this section. This is the meat and potatoes of chapter 14. Pretty much everything else in this chapter is applications of everything in this video. So you really need to make sure you have a clear understanding of how to do these integrals. And we'll do some more practice on Friday. So good luck, and I hope you took notes on this so that you have them to refer back to. And please don't hesitate to contact me if you have any questions. Have a great day.